Okay, so here we are at Charles's law. This law is going to look at how volume affects temperature and temperature affects volume. We're going to keep the pressure and the number of moles the same. So we find that volume and temperature are directly proportional. If the volume increases, so does the temperature. And we can write this equation. The initial volume divided by the initial temperature will be equal to the final volume divided by the final temperature. This is assuming that the pressure and the number of moles don't change. So let's look at this on our model. I have set this so that the pressure doesn't change. If I cool this system down, let's first look, pressure is 6.1, temperature is 113. I'm going to cool it down, temperature's falling, pressure is staying the same, the volume of the container is getting smaller. If I heat the system up, we're now at 29 degrees. If I heat it up, we'll see that the temperature is climbing. We're past 100 now, and the volume is getting larger. Pressure is staying constant. If I increase the temperature, does my balloon get larger or smaller? Okay, so what we've said is the temperature and pressure are directly proportional. So if the temperature increases, we expect the volume to increase. If the temperature decreased, the volume would decrease. So here we say we increase the temperature, the volume will increase, so my balloon is going to get larger. It's very important when working these calculations that all temperatures must be stated in Kelvin. The kinetic energy of the molecules is only proportional in Kelvin, not in Celsius. So let's work our first problem. Like we did with the other problems, we're first going to start with a table that helps us We're going to start with the table and get rid of all this. I do not know what I'm doing to all that. Okay, we'll start with the table. The volume is equal to 785 milliliters. The temperature is equal to 21 degrees Celsius. This will be our initial volume and temperature, because now it asks us if the temperature drops, so temperature 2 is going to be equal to 0 degrees Celsius. What is the new volume? What is the volume 2? And we don't know what that one is. I do see a problem. Before we do anything else, we need to take these temperatures and change them into Kelvin. We could do that very simply by adding 273 to them. So this is equal to 294 Kelvin, and this is equal to 273 Kelvin. Now our problem, our formula for this part is that V1 divided by T1 going to be equal to V2 divided by T2. Now the only one we don't have is this V2. That's the one we want to solve for. We want it to be by itself. And so we want to get rid of the T2. The easiest way to get rid of the T2 is to multiply both sides by T2. If you do that, these two will cancel out, and we're left with V2 alone on that side. So we can rewrite it better down here. We'll write V2 is equal to T2 V1 divided by T1. And then we've got our chart here. We can just fill in. T2 is 273 Kelvin. V1 was 785 milliliters. And we can divide by 294, which was the T1. If we do our math here, we'll end up with 729. This was Kelvin, and so with Kelvin on the top and Kelvin on the bottom, we're left with milliliters, which is good because we have a volume. It's good that we have milliliters. I've got one more problem. Sample of oxygen gas has a volume of 400. So let's just start. We have a volume of 420 milliliters and a temperature of 18 degrees Celsius. At what temperature? We don't know the second temperature. Will the volume, that's the secondary volume, be 640 milliliters? So these are our ones, and these are our twos. We're going to need to add 273 to our 18, and that will give us 291 Kelvin. And let's write our formula down. V1 divided by T1 is equal to V2 divided by T2. Now we have V1 and V2 and we have T1. We don't have, I'll do it in T2. So we need to solve our equation for T2. And I think the best way to teach you, to show you to do this, is to cross multiply. So if we cross multiply, we get T2 times V1 is equal to V2 times T1. All I've done is cross multiply. That gets rid of our unknown being in the denominator. So now we've got it all on a line and we can deal with it better. We are still going to need to get T2 by itself though. So we'll divide by V1, both sides. So we have V1's on this side we'll get rid of, and T2 will now be by itself. I'm going to rewrite it over here. T2 is equal to V2 T1 V1. Oops. That's V1. Okay, T1 V1. Okay. And then we can just substitute in. V2 was 640 milliliters. T1 is 291 Kelvin. And V1 was 420. This gives us 443 Kelvin. Now, we look back up here and it asks us at what temperature in Celsius will the volume of oxygen. So we need this to be in Celsius. We'll have to subtract off 273 to get us back into Celsius. And so it'll be 170 degrees Celsius. And that would be my answer.